They force us to reconsider not just what dark matter is, but what it might be doing. What these observations reveal suggests that dark matter is not the passive, invisible scaffolding we imagine, but something far more dynamic, far more pervasive, and far more intimately connected to our existence than we ever suspected. It's watching us. This phrase is not literal. Dark matter has no eyes, no consciousness, no intention, but it captures something profound about what telescopes have confirmed. Dark matter is not out there, distant and separate from our lives. It is here, passing through us at this very moment, permeating the space we occupy, threading through our bodies, our homes, our planet, and it is not merely present. It responds to the presence of ordinary matter. Clusters around galaxies and stars form structures that mirror and encompass the visible universe. We are embedded in dark matter. We move through it. It moves through us. We cannot see it, cannot touch it, cannot directly detect it, and yet it shapes the cosmos we inhabit, determines the structure of galaxies, influences the fate of the universe itself. I want to take you through what telescopes have actually confirmed, because understanding these findings requires appreciating both the history of dark matter research and the profound implications of what we now know. Let me start with what dark matter is, or rather what we know it is not. Dark matter is not ordinary matter. It is not made of protons, neutrons, and electrons, the building blocks of atoms, molecules, stars, and planets. It does not emit light, absorb light, or interact with light in any way. It is invisible not because it is too faint to see, but because it does not interact with electromagnetic radiation at all. Dark matter is not antimatter. Antimatter annihilates when it contacts ordinary matter-producing gamma rays. We see no such annihilation signatures from the vast quantities of dark matter that must exist. Dark matter is not black holes, at least not primarily. While black holes are dark and gravitationally significant, studies of gravitational lensing and cosmic microwave background have ruled out black holes as the dominant component of dark matter. Dark matter is not neutrinos, at least not ordinary neutrinos. Neutrinos are too light and move too fast to form the structures we observe. Dark matter must be cold, moving slowly enough to clump under gravity. What dark matter is remains unknown. We know it has mass. We know it interacts gravitationally. We know it does not interact electromagnetically. Beyond this, its nature is a mystery. This mystery has persisted for nearly a century. The evidence for dark matter was first noted in the 1930s, when astronomer Fritz Zwicky observed that galaxies in the Coma cluster were moving too fast to be held together by the visible matter alone. Something unseen was providing additional gravitational pull. In the 1970s, astronomer Vera Rubin confirmed this finding by studying the rotation of galaxies. She found that stars in the outer regions of galaxies were orbiting just as fast as stars near the center, a pattern that made no sense. If only visible matter were present, the galaxies were embedded in halos of invisible matter, providing the gravity needed to explain the observations. Since then, evidence for dark matter has accumulated from multiple sources: the cosmic microwave background, gravitational lensing, galaxy cluster dynamics, large-scale structure formation. The evidence is overwhelming. Dark matter exists, but what it is remains one of the greatest unsolved problems in physics. Now, let me describe what telescopes have recently confirmed about dark matter's distribution. Dark matter is not distributed uniformly through space. It is structured, clumped, organized into a vast cosmic web that mirrors and encompasses the visible universe. This structure was predicted by cosmological simulations and has now been confirmed by observations. Dark matter forms halos around galaxies, clusters around galaxy clusters, connects through filaments into a cosmic web that spans billions of light years. Recent observations have mapped this structure with unprecedented precision. The Dark Energy Survey using the Victor M. Blanco telescope in Chile has mapped the distribution of dark matter across large portions of the sky by measuring gravitational lensing, the bending of light from distant galaxies as it passes through intervening dark matter. The resulting maps show a complex filamentary structure with dense regions connected by bridges and surrounded by voids. The Hypersuprime Cam survey in Japan has produced complementary maps covering different regions of the sky with similar precision. The results agree. Dark matter forms a cosmic web, a vast network of structures that extends throughout the observable universe. The James Webb Space Telescope has contributed by observing galaxies at unprecedented distances, revealing the dark matter halos that surround them. Even the earliest galaxies forming when the universe was less than 1 billion years old are embedded in dark matter halos. The structure was present from the beginning. But the most striking confirmation involves the local distribution of dark matter, the dark matter in our own galaxy, in our own solar system, in our own neighborhood. We live inside a dark matter halo. The Milky Way galaxy is embedded in a dark matter halo roughly 10 times larger than the visible galaxy. This halo extends hundreds of thousands of light years from the galactic center, encompassing the stars, gas, and dust that we can see. The dark matter halo is not uniform. It has structure, density variations, streams, subhalos. The halo is dynamic, constantly evolving as dark matter flows in, orbits, interacts gravitationally with itself and with ordinary matter. Recent observations have mapped this local halo with increasing precision. The Gaia satellite, by measuring the positions and motions of over 1 billion stars, has revealed the gravitational influence of dark matter on stellar orbits. The data confirm that dark matter is present, is structured, and has particular density and velocity distributions. The local density of dark matter, the amount passing through our region of the galaxy, has been measured at roughly 0.3 GeV per cubic centimeter. This is a small amount by everyday standards, but it means that dark matter is constantly streaming through the Earth, through our bodies, through everything we know. Approximately 100,000 dark matter particles pass through every square centimeter of your body every second. You do not feel them. They do not interact with your atoms, your molecules, your cells. They pass through as if you were not there, as if you were transparent, ghost-like, insubstantial. But they are there. They are passing through you right now as you read these words. Dark matter is not distant. It is intimate, immediate, omnipresent. Now, let me describe what telescopes have confirmed about dark matter's influence on structure. The visible universe, the stars, galaxies, clusters we can see, did not form in isolation. It formed within a scaffolding of dark matter, guided by gravitational forces that dark matter provided. In the early universe, dark matter began to clump before ordinary matter could. Dark matter does not interact electromagnetically, so it was not held apart by radiation pressure as ordinary matter was. While ordinary matter was still a hot plasma bound to photons, dark matter was already collapsing into structures. These early dark matter structures became the seeds for later galaxy formation. When the universe cooled enough for ordinary matter to decouple from radiation, about 380,000 years after the Big Bang, ordinary matter fell into the gravitational wells that dark matter had already created. Galaxies formed where dark matter was dense. Voids formed where dark matter was sparse. The distribution of galaxies across the sky reflects the underlying distribution of dark matter, which itself reflects the tiny density fluctuations present in the early universe. Telescopes have confirmed this picture by observing the correlation between dark matter and visible matter. Gravitational lensing maps show that dark matter is concentrated where galaxies are concentrated. The cosmic web of galaxies traces the cosmic web of dark matter. The structure we see is a shadow of the structure we cannot see. But recent observations have revealed something more subtle and more disturbing. Dark matter does not merely provide the scaffolding for structure. It actively shapes the evolution of that structure. Dark matter halos grow over time, accreting more dark matter from their surroundings. They merge with other halos, combining into larger structures. They develop substructure, smaller halos orbiting within larger halos, remnants of past mergers. This evolution is dynamic, ongoing, continuous. The dark matter halo surrounding the Milky Way is not static. It is constantly changing, absorbing smaller halos, being shaped by its own internal dynamics and by interactions with neighboring halos. The Andromeda Galaxy, our nearest large neighbor, has its own dark matter halo. These two halos are already interacting, their outer regions overlapping, their gravitational fields influencing each other. In about 4.5 billion years, the galaxies will merge, and their dark matter halos will merge too, forming a larger combined structure. We are not merely embedded in dark matter, we are embedded in a dynamic dark matter structure that is actively evolving, interacting, changing around us. Now, let me describe what telescopes have revealed about dark matter's behavior on small scales. The large-scale predictions of dark matter cosmology have been spectacularly successful. The cosmic microwave background, the large-scale distribution of galaxies, the growth of structure over cosmic time, all match the predictions of cold dark matter models with remarkable precision. But on smaller scales, the scales of individual galaxies, and below, discrepancies have emerged. These discrepancies have been controversial, debated for decades, and recent observations have confirmed that at least some of them are real. The cusp core problem is one such discrepancy. Dark matter simulations predict that dark matter halos should have dense centers, cusps, where the density rises steeply toward the center. But observations of dwarf galaxies and low surface brightness galaxies often show flatter cores, where the density levels off. The missing satellites problem is another. Simulations predict that large galaxies like the Milky Way should be surrounded by thousands of small dark matter halos, each potentially hosting a dwarf galaxy. But we observe far fewer dwarf galaxies than predicted, a discrepancy of roughly an order of magnitude. The too big to fail problem is related. The largest predicted subhalos should be dense enough to host visible dwarf galaxies. But many of the observed dwarf galaxies are less dense than predictions suggest. Either the subhalos do not exist, or they are less dense than predicted. These small-scale problems have multiple possible explanations. Perhaps baryonic physics, the behavior of ordinary matter, including star formation, supernova feedback, and gas dynamics, modifies the dark matter distribution in ways that simulations have not fully captured. Perhaps dark matter has properties beyond simple, cold, collisionless behavior. Perhaps it self-interacts, or is warm rather than cold, or has other features not included in standard models. Recent observations have constrained these possibilities. Studies of gravitational lensing on small scales have measured the abundance of subhalos, finding results consistent with cold dark matter predictions, but with significant uncertainties. Studies of dwarf galaxies have probed the inner density profiles of dark matter halos, finding a range of behaviors that may reflect the diversity of galaxy formation histories. What telescopes have confirmed is that dark matter behaves differently on small scales than simple models predicted, or that our models of galaxy formation are incomplete, or both. The small-scale behavior of dark matter remains an active area of research, with new observations continuously refining our understanding. Now, let me describe what telescopes have revealed about dark matter's interaction, or lack thereof, with ordinary matter. Dark matter, by definition, does not interact electromagnetically. It does not emit light, absorb light, or scatter light. This is why it is dark, invisible to all our telescopes that operate across the electromagnetic spectrum. But might dark matter interact in other ways? Might there be forces beyond gravity and electromagnetism through which dark matter could couple to ordinary matter? This question has motivated decades of experimental searches. Underground detectors have sought to catch dark matter particles scattering off atomic nuclei. Particle colliders have sought to produce dark matter in high-energy collisions. Space telescopes have sought gamma rays or other signals from dark matter annihilation. So far, all these searches have come up empty. Dark matter has not been directly detected despite enormous experimental effort. The constraints on dark matter interactions have tightened year by year, ruling out many theoretical possibilities. Recent observations have added to these constraints. Studies of galaxy clusters where dark matter and ordinary matter are separated by mergers have constrained dark matter self-interactions. When clusters collide, ordinary matter, mostly hot gas, collides and slows down, while dark matter, if it is collisionless, passes through unimpeded. By measuring the separation between gas and dark matter, astronomers can constrain how strongly dark matter interacts with itself. The results show that dark matter self-interactions must be weak at most, comparable to the weak nuclear force, perhaps much weaker. Dark matter is not merely invisible to light, it is nearly invisible to itself. Studies of the cosmic microwave background have constrained dark matter interactions with ordinary matter in the early universe. If dark matter had coupled to the primordial plasma, it would have left imprints on the CMB that we do not observe. The constraints require that any such coupling be extremely weak. Studies of stellar populations have constrained dark matter interactions with atoms. If dark matter scattered off atoms in stars, it could transport energy from the stellar core to the surface, affecting stellar structure and evolution. The absence of such effects in observed stars constrains the interaction strength. All these observations point to the same conclusion. Dark matter interacts very weakly with ordinary matter, if at all. It is not merely invisible but intangible, present all around us but unable to touch us, passing through us without effect. This intangibility is what makes dark matter so difficult to study and so disturbing to contemplate. We are surrounded by something we cannot see, cannot touch, cannot detect directly. Something that nonetheless exerts gravitational influence on everything we can observe. Now, let me describe what makes these confirmations terrifying. The phrase, "it's watching us," is, as I said, not literal. Dark matter has no awareness, no consciousness, no intention, but the phrase captures something real about our situation. Dark matter is pervasive. It is not concentrated in distant galaxies or remote corners of the universe. It is here, in our solar system, in our planet's vicinity, passing through our bodies at this moment. We are immersed in it, surrounded by it, penetrated by it. Dark matter is influential despite being invisible and intangible. It shapes the universe we inhabit. Galaxies form where dark matter tells them to form. Stars orbit where dark matter's gravity directs them. The large-scale structure of the cosmos reflects the large-scale structure of dark matter. Dark matter is mysterious. After nearly a century of evidence, we still do not know what it is. Our best theories, WIMPs, axions, sterile neutrinos, remain unconfirmed. Our most sensitive experiments have found nothing. The nature of dark matter remains one of the deepest mysteries in physics. Dark matter is dominant. There is roughly 5 times more dark matter than ordinary matter in the universe. We, our bodies, our planet, our sun, all the stars and galaxies we can see, are the minority. We are embedded in a cosmos dominated by something we cannot observe, cannot understand, cannot explain. This is terrifying in a deep sense. We like to think that we understand the world we inhabit, that science has revealed the nature of reality, that we know what surrounds us and what we are made of. Dark matter challenges this confidence. It reveals that most of the universe is invisible to us, that we are surrounded by something unknown, that our understanding is fundamentally incomplete, and yet dark matter is not distant. It is not an abstract cosmological curiosity relevant only to the early universe or to distant galaxy clusters. It is here, now, everywhere. The unknown is not remote, it is intimate. Now let me describe what recent observations have revealed about dark matter's dynamics. Dark matter is not static. It moves, flows, orbits, interacts gravitationally with itself and with ordinary matter. The dark matter halo surrounding the Milky Way is in constant motion, with particles orbiting the galactic center, streaming through the solar neighborhood, responding to gravitational perturbations. Recent observations have begun to map these dynamics with unprecedented precision. The Gaia satellite, by measuring the positions and velocities of over 1 billion stars, has revealed the gravitational influence of dark matter on stellar motions. Stars in the Milky Way do not orbit in perfect circles. Their orbits are perturbed by the gravitational pull of dark matter structures, both the smooth halo and the subhalos within it. By analyzing these perturbations, astronomers can infer the distribution and dynamics of dark matter. The results reveal a complex picture. A smooth background halo, streams of dark matter from disrupted subhalos, density variations from ongoing accretion. One particularly striking discovery involves the Gaia sausage, or Gaia Enceladus, the remnant of a dwarf galaxy that merged with the Milky Way roughly 10 billion years ago. This merger deposited not only stars but also dark matter into the Milky Way's halo. The stars from this merger can be identified by their distinctive orbits. The dark matter that accompanied them cannot be seen directly but can be inferred from gravitational modeling. The Gaia sausage dark matter is on highly elongated orbits passing through the solar neighborhood with velocities and directions different from the smooth background halo. This affects the flux of dark matter particles passing through the Earth and therefore affects the prospects for direct detection experiments. Other streams and substructures have been identified as well. The Milky Way's dark matter halo is not smooth, but lumpy, with overdensities and underdensities reflecting its complex merger history. This dynamic, structured dark matter environment is what surrounds us. We are not in a uniform sea of dark matter, but in a complex, evolving structure with streams, subhalos, and density variations passing through our neighborhood. Now, let me describe what observations have revealed about dark matter in our solar system. The question of dark matter in the solar system has been debated for decades. Does dark matter accumulate around the sun? Does it affect planetary orbits? Could it be detected locally? The answer, according to current understanding, is that dark matter is present but not concentrated in the solar system. The solar system passes through the galactic dark matter halo, intercepting whatever dark matter happens to be in its path. But the solar system does not significantly accumulate or concentrate dark matter. The sun's gravity is not strong enough to capture significant amounts. Recent observations have constrained the density of dark matter in the solar system's neighborhood. Analysis of planetary orbits, particularly the precession of planetary perihelia, has set upper limits on how much dark matter could be present without affecting observed motions. The limits are consistent with the expected galactic dark matter density, providing no evidence for local concentration. But the galactic dark matter density itself means that dark matter is constantly passing through the solar system. The Earth orbits through this dark matter wind, encountering a stream of particles that flows through the planet and everything on it. The velocity of this dark matter wind depends on the Earth's motion through the galaxy. As the Earth orbits the Sun and the Sun orbits the galactic center, our velocity relative to the dark matter halo varies. This variation produces an annual modulation in the expected dark matter flux, a signature that direct detection experiments have sought. Some experiments have claimed to detect this annual modulation. The Dama Libra experiment in Italy has reported a statistically significant annual modulation for over 2 decades. But other experiments with different detector technologies have not confirmed this signal. The situation remains controversial with no consensus on whether dark matter has been directly detected. What is not controversial is that dark matter is passing through the solar system, through the Earth, through us. Whether we can detect it remains uncertain. That it is present is not. Now let me describe what observations have revealed about dark matter's role in cosmic evolution. Dark matter has shaped the universe from its earliest moments to the present day. Its gravitational influence has driven the formation of structure, guided the assembly of galaxies, determined the large-scale architecture of the cosmos. Recent observations have traced this influence across cosmic history. In the early universe, tiny density fluctuations imprinted during inflation and visible in the cosmic microwave background provided the seeds for structure formation. Dark matter amplified these fluctuations, collapsing into halos, while ordinary matter was still bound to radiation. After recombination, when ordinary matter decoupled from radiation, ordinary matter fell into the dark matter halos, forming the first stars and galaxies. The locations of these first galaxies were determined by the locations of dark matter halos. The masses of the first galaxies were determined by the masses of the halos that hosted them. As the universe evolved, dark matter halos grew through accretion and merging. Small halos merged to form larger halos. Galaxies within these halos merged to form larger galaxies. The hierarchical assembly of cosmic structure was driven by dark matter gravity. Telescopes have observed this process at various stages. The cosmic microwave background reveals the initial conditions. Galaxy surveys reveal the distribution of structure at various epochs. Gravitational lensing reveals the dark matter distribution directly without relying on visible tracers. The picture that emerges is one of dark matter as the architect of the cosmos, the invisible framework within which all visible structure has formed. Without dark matter, galaxies would not exist. Stars would not form. We would not be here. This is terrifying because it reveals our dependence on something we do not understand. Our existence depends on dark matter. Dark matter shaped the environment in which we evolved. Dark matter continues to surround and permeate us, and yet we do not know what it is. We are dependent on the unknown. Our existence is contingent on a mystery. In part 2, I want to explore the deeper implications of these observations, what they suggest about the nature of dark matter, the possible explanations for its properties, and what it would mean if dark matter turns out to be something even stranger than current theories suppose. So, we've established what telescopes have confirmed about dark matter: its pervasive presence throughout the cosmos, its dynamic and structured distribution, its intimate proximity to our lives, its dominant role in shaping the universe. We've seen that dark matter is not distant or abstract, but immediate and omnipresent, passing through our bodies at this very moment. Now, I want to explore the deeper implications of these observations. What might dark matter actually be? What do the observations tell us about its properties? And what are the most disturbing possibilities suggested by what we have learned? Let me begin by examining the leading theoretical candidates for dark matter. The most popular candidate for decades has been the WIMP, the weakly interacting massive particle. WIMPs are hypothetical particles that interact through gravity and the weak nuclear force, but not through electromagnetism or the strong force. They would be produced in the early universe and would naturally have the right abundance to explain dark matter if their mass is roughly 10 to 1,000 times the mass of a proton. This WIMP miracle, the coincidence that weak-scale physics naturally produces the right dark matter abundance, made WIMPs the leading candidate and motivated decades of experimental searches, but the searches have found nothing. Underground detectors have achieved extraordinary sensitivity, capable of detecting a single WIMP scattering off a single nucleus in a ton of material. They have seen no signal. The parameter space for WIMPs has shrunk year by year as experiments have improved. Particle colliders have searched for WIMPs produced in high-energy collisions. They have seen no signal. The Large Hadron Collider has ruled out many WIMP scenarios that were considered promising. Indirect detection experiments have searched for gamma rays, neutrinos, or antimatter from WIMP, annihilation in the galactic halo, or in the Sunday. They have seen no convincing signal. The absence of detection does not rule out WIMPs entirely. Parameter space remains and experiments continue to improve, but the WIMP miracle has lost some of its luster. Many physicists now consider other candidates equally or more plausible. Axions are another leading candidate. Originally proposed to solve a problem in particle physics, the strong CP problem axions would be extremely light particles, perhaps 10 to the power of -5 to 10 to the power of -3 electron volts. They would be produced in the early universe through a different mechanism than WIMPs and would behave as cold dark matter despite their low mass. Axion searches use different techniques than WIMP searches. The most sensitive experiments look for axion conversion to photons in strong magnetic fields. Results so far have been null, but only a fraction of the parameter space has been explored. Sterile neutrinos are another possibility. These would be heavier cousins of the known neutrinos interacting only through gravity. They would be warm dark matter, moving faster than WIMPs but slower than ordinary neutrinos. Warm dark matter would suppress small-scale structure, potentially explaining some of the discrepancies between observations and cold dark matter predictions. Primordial black holes have been reconsidered as dark matter candidates. If black holes formed in the early universe before stars existed, they could contribute to dark matter. Various observations constrain the allowed mass ranges, but windows remain, particularly for black holes with masses comparable to asteroids. More exotic possibilities have been proposed. Dark photons, dark sectors with their own forces and particles, fuzzy dark matter consisting of ultralight particles with wavelengths comparable to galaxies, self-interacting dark matter that collides with itself but not with ordinary matter. What telescopes have confirmed is that dark matter behaves in certain ways. It is cold or warm, not hot. It is largely collisionless. It clusters on certain scales. These behaviors constrain the possibilities but do not uniquely identify the particle. Now, let me examine what observations have revealed about dark matter's fundamental properties. The observations constrain dark matter in multiple ways. Dark matter is stable or nearly stable. It has persisted since the early universe, roughly 13.8 billion years. Any dark matter particle must have a lifetime far exceeding the age of the cosmos. Dark matter is cold. Its velocity dispersion is low enough to allow structure formation on the scales we observe. Hot dark matter particles moving near the speed of light would erase small-scale structure. We do not observe this erasure. Dark matter is largely collisionless. When galaxy clusters merge, dark matter passes through without significant interaction. The constraints from cluster mergers require that dark matter self-interactions be weak, comparable to or weaker than weak nuclear interactions. Dark matter does not significantly annihilate. If dark matter particles annihilated with each other at high rates, we would see gamma rays or other products. The absence of clear signals constrains the annihilation cross-section. Dark matter does not significantly decay. If dark matter decayed into visible particles, we would see the products. The absence of signals constrains the decay rate. These constraints paint a picture of dark matter as extraordinarily inert, stable, cold, collisionless, non-annihilating, non-decaying. It does nothing except gravitate. It is the most passive, most invisible, most intangible substance imaginable. And yet, it dominates the universe. 5 times more abundant than ordinary matter, shaping the cosmos, determining the fate of galaxies, surrounding us at every moment. This combination, dominance and passivity, ubiquity and invisibility, is deeply strange. Dark matter is the most important stuff in the universe and the most undetectable. It shapes everything and touches nothing. Now let me examine what observations have revealed about dark matter's distribution on the smallest scales. The small-scale distribution of dark matter is where the most interesting discrepancies arise and where the most disturbing possibilities lurk. On large scales, cold dark matter models work beautifully. The cosmic microwave background, the large-scale distribution of galaxies, the growth of structure over cosmic time all match predictions with impressive precision. On small scales, the scales of individual galaxies and below the match is less perfect. The cusp core problem mentioned earlier is one discrepancy. Simulations predict cuspy dark matter halos with density rising steeply toward the center. Observations of dwarf galaxies often show chord profiles with density leveling off at the center. Recent observations have refined this picture. Not all dwarf galaxies have cores. Some do show cuspy profiles. The diversity suggests that galaxy formation, processes star formation, supernova feedback, gas dynamics may modify dark matter distributions differently in different galaxies, but the diversity itself is not fully explained. Why do some galaxies have cores and others cusps? What determines the inner structure of dark matter halos? One possibility is that dark matter has properties beyond the standard cold collisionless model. Self-interacting dark matter that scatters off itself, exchanging energy and momentum, would naturally produce cores. The self-interactions would thermalize the inner halo, erasing the cusp and producing a uniform density core. Recent observations have tested this possibility. Studies of galaxy clusters where self-interactions would have the strongest effects have found evidence that is tantalizingly ambiguous. Some clusters show offsets between dark matter and galaxies that could indicate self-interactions. Others show no such offsets. The constraints require that if dark matter self-interacts, it does so with a cross-section comparable to atomic scales, roughly 1 square centimeter per gram. This is weak by particle physics standards, but significant by gravitational standards. If dark matter self-interacts at this level, it would have profound implications. It would mean dark matter has its own physics, its own forces, perhaps its own complexity. Dark matter would not be a single inert particle, but a sector, possibly with multiple species, possibly with interactions we have not imagined. Now, let me examine what observations have revealed about dark matter substructure. Dark matter halos are not smooth. They contain subhalos, smaller concentrations of dark matter orbiting within the larger halo. These subhalos are remnants of smaller halos that were accreted as the main halo grew. The abundance and properties of subhalos are sensitive to dark matter physics. Cold dark matter predicts abundant substructure down to very small scales. Warm or self-interacting dark matter would suppress substructure, erasing small halos. Recent observations have probed substructure through multiple techniques. Gravitational lensing is one technique. When light from a distant source passes through a galaxy, it is bent by gravity. If the galaxy contains subhalos, these produce additional distortions, small perturbations in the lensed image that reveal the presence of substructure. Several studies have detected substructure through lensing. The results suggest that subhalos exist with masses down to roughly 10 million solar masses, consistent with cold dark matter predictions. But the measurements are difficult and systematic uncertainties remain. Stellar streams provide another probe. When a dwarf galaxy or globular cluster is torn apart by tidal forces, its stars spread into a stream that traces the orbit. If this stream passes near a dark matter subhalo, the gravitational encounter produces gaps and perturbations in the stream. Studies of stellar streams in the Milky Way have found evidence for such perturbations. The PAL5 stream, for example, shows gaps that could be produced by encounters with dark matter subhalos. The GD1 stream shows similar features. These observations suggest that dark matter subhalos exist, and that the Milky Way's halo contains thousands of them.